Hello again. It's still June 9th. I'm wearing a different outfit. I filmed the last video yesterday, and today for me is genuinely June 9th now. And I found out a way to solve this and think about solving it without needing to rely on a large calculator like Wolfram Alpha to calculate all those digits for us. It comes from the idea of investigating this through the binomial theorem, and let's get into it. So let's look at the binomial theorem for a sum. It's going to be some binomial, a plus b to the power of some exponent. I'm just going to call that c. And to write this with the binomial theorem, we would sum up from k to 0, or k from 0 to c, that exponent. We're going to have our binomial coefficient here, which is c choose k. And then I'll have the first term to the power of c minus k times the second term to the power of just the k. So this is just some kind of formula that you can use to expand out binomials to high powers. And that's kind of what we're doing here, right? We have a binomial to a large power. The next thing that I want to do is write out the binomial theorem for a difference. And it's going to look pretty much the same. We're going to still go from k equals 0 to c. We're still going to have the same binomial coefficient. And the first thing with the exponents on it, the base is still going to be the same because it's still just a. So the only part that's different is we're going to have a negative b here because, we're multiplying a whole bunch of minus b's instead of plus b's. That's really going to be the only thing different between these two binomial theorem formulas. And I want to investigate what happens when we add these two together. And so I'm actually going to put a plus sign between these two. So these two sums are going to be nearly identical, right? They essentially look exactly the same. The only difference is that we have a negative sign in this b right here. So if you imagine k being even and we raised b to some even, or negative b to some even power, we're eventually just going to get the same thing as b to the k, as long as k is even. If k is odd, then we will get some kind of negative sign out of that. And then this one will actually be the exact opposite, like the negative opposite of the term that we have from the left sum. So as we add these two sums together, anytime k is odd, the terms are going to cancel out. And anytime k is even, we're just going to get two of the same number. So to express that idea, and I don't know if this notation is used, but I want to say k equals 0 and then k is even. I guess I could do something like, k equals 2z where z is an integer or something. I'll just say k is even. And that's still going to go all the way up to c. We're going to do c choose k. And I'm going to omit the negative sign because, again, I'm assuming that k is even here. And so I'll always create that kind of positive version of b to the k. Oh, and then I said it would add to itself, right? So these terms and these sums are going to be identical when k is even. So I will do 2 times, just like that. And so now when we add this binomial theorem to that one, we're going to get whatever sum I have down here. And essentially, the really important part that I want to prove is that this is always going to be an integer. Because, for our specific problem, this is also always going to be an integer. Like, if you assume that a and b are integers, then great. I think this is pretty clearly always an integer, because when you do multiplication with integers, you get integers. Here's more multiplication. The choose function always returns integers for c and k as integer inputs. We're adding up a whole bunch of integers, so great, still integers, and then finally multiplying by 2. So when a and b are integers, this is very clearly an integer. And it's a little bit more trouble when we finally sub in the actual values that we're using today, the 17 and the square root of 280, because this isn't a perfect square. So this is an irrational number. But fortunately, if we kind of do some substitutions here, I am going to put, here's the same 2, sum, c, and then k equals 0 to c, k is even. This k is even condition means that once I sub in this b, this root 280, I'm going to raise it to some even power. Let's say 2L, I don't know, k equals 2L. L is just some integer, and this is just kind of demonstrating that we do definitely have an even power on the right side, and therefore this number is going to just be 280 to the power of some other integer. And so we're back into this case where our binomial theorem, once we do this positive binomial theorem, this negative binomial theorem, and then add up all the terms together, we're going to get an integer. And so with this general idea, I'm really confident that I can write, 17 plus root 280 to the power of 17, and then plus the conjugate, 17 minus root 280 to the power of 17, is some kind of integer. Because once we do the binomial theorem and that some terms cancel out, we're always left with just some whole numbers. And, I don't really know what this integer is. Honestly, it's probably going to be, it's going to be almost the size of this. Because, how earlier we said that, this number here is like 33.7. So, here's like the 33.7 that we were working with. But then the number on the right side is going to be kind of small. I'm just kind of pulling out my calculator real quick because I forget the approximate value for the square root of 280. But when we do the difference, we're going to get some kind of decimal, which is, I'll just say 0.3, honestly, just to kind of keep the same amount of decimal places. And it'll still prove my point. I know I'm rounding heavily, and in the previous video, I said something about how, estimating won't help. But here, it's totally fine. So this is kind of like a representation of what we're doing here. And if you notice, the term on the left gets really, really big, right? Because we're doing like 34 multiplied to itself over and over and over again. On the right side, we're going to get something like freakishly small, right? So close to zero. Because once we do it like the 17th power of a number that's below 1 and above 0, we're going to get some number that is so tiny. To even prove my point, I want to do to the power of 17 on this. And look how many zeros there are in front of that number. This is a teeny number, so close to 0. And so this very, very large number plus this teeny tiny number is going to be equal to an integer. So I'll just say is an element of the integers. And you know what? I think I actually want to do some math on this integer. So I will say it's equal to, let's just say z for some integer z. I know it's usually used for complex numbers. Sorry. But here's where we're finally going to find our solution. This massively big number plus this teeny tiny number super close to 0 is proved to be an integer. So once I take the value that we're looking at today and isolate it, we're going to get that big number equals an integer minus something so small, right? This is a number essentially close to 0. So we're going to get some kind of integer component and then a whole bunch of 9s. Basically, we're going to have the same amount of 9s as we see zeros here. I mean, maybe give or take one. And there's going to be a whole bunch of 9s, basically just kind of showing that this number being close to 0 is the same thing as this number being close to the integer right above it. And so that's this number right here. Once we take this number and isolate it, we get an integer minus a number that we both know is so close to 0. And subtracting this one away is going to give us a decimal expression at the end with a whole bunch of 9s. And so that, to me, is my proof. And I didn't see that yesterday, and I saw it now today, and I'm happy to share before it hits midnight in my time zone. And that is going to be my proof that the 10th digit and, many digits thereafter are going to be all 9s. So thanks for watching. Hopefully you found this second video, this follow-up to the first one, and hopefully it kind of clarifies some more strategies for solving quite an interesting problem. Alrighty. I'll see you tomorrow. Bye bye.